All right, so today we're going to look at this problem that we were working on Monday's class meeting. A couple of more different ways just to illustrate the different types of techniques that we can apply in the frequency domain. So another way that we could potentially work this circuit, I believe to this point we've done mesh analysis and superposition. So another way that we could solve this circuit pretty easily would be using the Thevenin equivalent circuit. And then once we find the Thevenin equivalent circuit, we can easily do just voltage division to figure out what our voltage VL is, okay? So our Thevenin equivalent circuit for this particular network, we're finding it with respect to our J20 ohm inductor there in the middle. So we're going to need to take that out. So we're going to have our 16 angle 0 degrees volt source on the left-hand side. Here is our 8 ohm resistor. Here's the open circuit terminals where our J20 ohm inductor was taken out. Here is our minus J 5/8 of an ohm capacitor. Here is our 2 angle negative 45 degrees ampere current source. Okay. So what I'm going to do is I'm going to write a Kirchhoff's voltage law loop around Kirchhoff's voltage law equation around this loop. And I am going to say that the voltage drop across my 8 ohm resistor will be V8 with this polarity. I'm choosing that particular polarity because I know that all 2 angle negative 45 degrees amperes of current will be flowing into the positive polarity terminal. So when I write my KVL equation, I will have negative 16 angle 0 degrees volts minus V8 plus VTH is equal to 0. From this, VTH is equal to 16 angle 0 degrees volts plus V8, where V8 is 8 ohms times 2 angle negative 45 degrees amps. And if I throw this into my calculator, the wrong parentheses, there we go. I get 29.564 angle negative 22.5 degrees volts. Our Thevenin equivalent resistance from the perspective of our inductor is found by looking at our dead network. So our voltage source is turned off. Here's our terminals we're going to be looking into. Minus J, sorry, 5/8 of an ohm. These open circuit terminals on the right-hand side are from turning off our current source. And so we're looking in here to find Z Thevenin. And it should be pretty obvious that Z Thevenin is simply our 8 ohm resistor, right? just so that we're super clear on why that is, I'm going to label these terminals A and B. I'm going to identify some nodes. So here's node A. Everything in green here is node B. And then here is another node to the right, which we could call node C for lack of a better label. Between A and B, we only see the 8 ohm resistor. The minus J 5/8 ohm capacitor isn't part of a closed loop, so it cannot contribute to the Thevenin equivalent resistance. Okay. So now we know what our Thevenin equivalent circuit is. So we have VTH here. VTH here. And we're going to connect our J20 ohm inductor over which our voltage VL that we're interested in occurs. And using voltage division, VL is simply VTH times J20 ohms over VTH plus J20 ohms. If I substitute in my numerical values, I get, let's see, 20 I over 8 plus 20. 27.450 angle negative 0.699 degrees volts. The exact same result we've gotten every other way we've worked it. Now let's look at it from a Norton equivalent circuit perspective. Rajan, how may I help you? Absolutely. All right. So another technique that we could possibly use, just really at this point giving you refreshers, would be to use the Norton equivalent circuit. Now, obviously, we could do a source transformation on the Thevenin equivalent we just found to get the Norton equivalent circuit, but that's no fun. So we're going to actually find I Norton. So our Norton current is going to be found by replacing the J20 ohm inductor with a short circuit. And then we're going to find the current flowing through that short circuit. So here's our short. This is our Norton phasor current. And I can find this phasor current by applying Kirchhoff's voltage law at this node. So effectively, I'm saying that this current flowing in plus this current flowing in has to equal this current flowing out of the node, which happens to be I Norton. So writing that KCL expression, I get I Norton is equal to 16 angle 0 degrees volts divided by 8 ohms plus 2 angle negative 45 degrees amps. Throw this into my calculator. So 16 over 8 is going to look like 2 plus 2 angle negative 45. Looks like 3.696 angle negative 22.5 degrees amps. Since we already know what our Thevenin equivalent impedance is, our Norton equivalent circuit would look like this. So we'd have I Norton in parallel with ZTH in parallel with our J20 ohm inductor, and the voltage drop VL is the voltage drop over the J20 ohm inductor. Using Ohm's law, VL would be I Norton times ZTH in parallel with J20. So that's going to be ZTH times J20 ohms over ZTH plus J20 ohms. So let's see, 8 times at 27.450 with an angle of negative 0.699 degrees volts. Again, the exact same result. We have now worked this problem 4 different ways, all of which yielded the exact same answer. Let's do it a 5th and final time with what I believe is actually the easiest way to do it. Let me know when you're ready for me to change the page or whatever. All right. So here's my circuit. I am going to do a modified nodal analysis, which we have not yet done. Okay. So I'm going to assume that this node is my ground. I'm going to put this in quotes as nodal. So the nodal voltage here is the exact same thing as VL, because our nodal voltage is measured with respect to ground. And the voltage drop over our inductor is the potential difference between that top middle node and ground. So those two quantities are actually the same thing. So I'm going to use them interchangeably. All right. So applying Kirchhoff's current law at that node, I'm going to have VL minus 16 angle 0 degrees volts divided by 8 ohms. So that's the current flowing to the left. I'm going to have VL over J20 ohms. That's the current flowing down. And the current flowing to the right is negative 2 angle negative 45 degrees amps. Set this equal to 0. And now it's just algebra. Okay. So I'll have VL times a factor of 1 over 8 ohms plus 1 over J20 ohms. And that will be equal to 16 angle 0 degrees volts over 8 ohms plus 2 angle negative 45 degrees amps. And thus VL is 16 angle 0 degrees volts over 8 ohms plus 2 angle negative 45 degrees amps divided by 1 over 8 ohms plus 1 over J20 ohms. I'm going to throw this in my calculator. Actually, kind of don't even need to. The reason why I say that is the numerator on the right-hand side of this is that Norton equivalent current that we determined earlier. And 1 over 8 ohms plus 1 over J20 ohms is the same thing as 8 ohms in parallel with J20. So the math that we're doing right here, and you can throw this in your calculator to verify, is actually literally this exact same math. We just came to it in a different way. But just to make sure, let's throw it into our calculator. 16 angle 0 over 8 plus 2 angle negative 45. All of this over 1 over 8 plus 1 over 20 I. And we get 27.450 angle of negative 0.699 degrees. Okay. So we have employed 5 different methods to solve this circuit, all of them yielding the exact same result. Okay. The reason why I showed you all 5 different methods is to illustrate that we're doing nothing more than applying our DC circuit analysis techniques here to these steady state sinusoidal circuits, analyzing them like we've done in numerous classes at this point, and getting the result that we're looking for. B, I wanted to illustrate all the different ways that I could think of to do this, to let you know that you can analyze these circuits in any way that you feel comfortable. There isn't a specific way that you need to do any of this stuff. So if you prefer to use mesh analysis, go ahead and use mesh analysis. If you prefer nodal, use nodal. If you want to use KCL, KVL, Ohm's law relationships, you can do that too. You can do source transformations, you can do Thevenin and Norton equivalent circuits. Any way that you can think of to analyze these circuits is absolutely applicable. You just need to apply the circuit theory correctly. Okay. All right, so we are now going to talk about something arguably new. If I can find engineering paper, there we go. Dad already had it open, so let me just delete this stuff from circuits 1 from yesterday. Remove annotations. There we go. All right, so there may be times in your engineering career when you deal with a circuit that is being excited at multiple angular frequencies. Okay, so let's take, for example, this circuit where we have some time domain voltage Vs of t, Let's call this a 15 ohm resistor. Throw a current source in here, IS of T. Let's call this a 0.5 Henry inductor. And let's throw a capacitor here. Let's call this a 0.1 farad capacitor. And we want to know, let's say arbitrarily, what the current flowing through this 15 ohm resistor is as a function of time, IRT. In this particular circuit, Vs of t is 20 cosine 3t plus 10 degrees volts. And Is of t is going to be 2 cosine 5t plus 60 degrees amperes. Notice that our two sources are operating at different angular frequencies. So this presents a problem. And the problem it presents is we know that the impedance of a resistor, ZR, is just equal to R. So everything's okay with our resistors. The impedance of an inductor is given by J omega L. Well, we have two different omegas that we have to concern ourselves with. And the impedance of a capacitor is given by 1 over J omega C. Again, we have two different omegas that we have to deal with. So to analyze a multi-frequency circuit like this, we are going to have to employ superposition, but we're going to do superposition effectively at one frequency at a time, okay? So all of our sources that are oscillating at an angular frequency of 3 radians per second we'll handle in one analysis, and then we'll look at it if the circuit is oscillating at, or with the sources on that are oscillating at 5 radians per second, and then go from there. If there were more than 2 frequencies, we would have to do more than 2 instances of superposition, okay? So analysis number 1, omega is equal to 3 radians per second. This is the same as effectively voltage source on and current source off. Okay. So when omega is equal to 3 radians per second, we are going to have our voltage source, which is going to look like 20 angle 10 degrees volts. We have our 15 ohm resistor. Our current source is turned off. We do that by replacing it with an open circuit. Here we have our 1/2 Henry inductor, which at an angular frequency of 3 radians per second has an impedance of 3 times 0.5, so that's J 1.5 ohms. And then here we have our capacitor. So 0.1 times 3 is going to look like 0.3. So 3/10. So I believe this is negative J 10/3 ohms. I'm going to double check that just to be safe. Yep, 10/3. And here is our frequency domain current I of R that we're looking for. So how would we solve for this current IR prime? Anybody have an idea? How, with this circuit at omega is equal to 3 radians per second, how could we solve for the current IR prime? Absolutely right. So effectively, Rygen suggested that we use Ohm's law, where the total voltage drop 20 angle 10 degrees volts occurs over all 3 of those impedances, which are connected in series effectively. So IR prime would be 20 angle 10 degrees volts divided by 15 ohms plus J 1.5 ohms minus J 10 over 3 ohms. I'm going to throw this into my calculator. I get a current of 1.323 angle 16.968 degrees. I'm going to give myself a little bit of room here before I do our second analysis, and you'll understand the reason here in just a moment. So our second iteration of superposition is when omega is equal to 5 radians per second. Effectively, our voltage source will be off and our current source will be on. So in this case, our voltage source being off looks like a short circuit. Here we have our 15 ohm resistor. We need the phasor value for our current source, which I'm going to have to scroll up. So it's going to look like 2 angle 60 degrees. We're going to have J times 5 times half a Henry now. So this is going to look like J 2.5 ohms. And our capacitor is going to look like, I believe it's minus J2. Again, just to make sure, I'm going to double check that. So 1 over 0.1 times 5. Yep. And our current of interest is this current IR double prime. So how might we solve for IR double prime here? Current division is actually the way that I would solve this, okay? Because I have a current source, 2 angle 60 degrees amperes in parallel with a branch containing a 15 ohm resistor in parallel with a branch containing that inductor and capacitor. So current division is absolutely the way that I would go with this. So we will have IR double prime. So one thing that I want to point out here This current is going to flow up and then it's going to split. So the expected direction of our current would be the current flowing through the resistor would be from right to left. IR is defined from left to right. So I'm just saying we're going to need to include a negative sign here. Okay. So we're going to have negative 2 angle 60 degrees amps times 1 over 15 ohms divided by 1 over 15 ohms plus 1 over J 2.5 minus J 2 ohms. So throwing that into my calculator, 1 over 15 plus 1 over 0.5 I, 2.5 minus 2 is 0.5. I get 0.067 angle negative 31.909 degrees. All right, yes. Yes, negative 31.909. All right, so here is where a very common mistake can be made, okay? In all of our prior dealings with superposition, we have simply added the results together, right? So we might be inclined to say that IR is simply IR prime plus IR double prime in this case, because that's what we've done every other time we've used superposition. But in a multi-frequency circuit, this is invalid, right? And the reason why it's invalid is because this phasor is operating at omega is equal to 5 radians per second. And this phasor is operating at omega is equal to 3 radians per second. Since they have different angular frequencies, adding them up in the frequency domain doesn't actually mean anything. It's incorrect, okay? So instead, we'd have to go to the time domain. IR prime is going to be 1.323 cosine 16.968 degrees amps. IR double prime of T is going to be 0.067, excuse me. Cosine negative 31.909 degrees amps. And IR of T, IR prime plus IR double prime. So effectively, in a multi-frequency circuit, we have to go back to the time domain before we can combine our results. And so what this is going to give us, kind of running out of room here, so I'll sneak it in, 1.323 cosine 3t plus 16.98 degrees. So 16.968 degrees, I think. Let me double check there. Yeah. Plus 0.067 times the cosine. Sorry, I made a mistake here. That should have been 5T minus 31.909 degrees amps. And this result cannot be simplified, okay? Because the sinusoids are oscillating at two different frequencies, we can't lump them together and make them look like a single sinusoidal signal, like we could if they were oscillating at the same frequency. Okay. All right, so that is all that I had prepared to talk about today. We still have a good half hour left of class. If you guys have any questions or want me to review any other type of circuit analysis, I'm happy to either make up a problem or find a problem to do it. If not, what we are going to be doing on Friday is getting into our power relationships. So we're going to talk about instantaneous power and average power for sure. And then we're going to introduce some, that's a review from circuits 1. And then we are going to introduce what's called the maximum average power transfer theorem, which will be new. Then next Monday, we are going to talk about power in multi-frequency circuits, instantaneous power and average power in multi-frequency circuits, which is a new topic. Then we are going to talk about effective values for currents and voltages, which is review. And then we're going to get into our complex power relationships next Wednesday, and that'll effectively wrap up our steady state sinusoidal analysis. So largely review of what we did in circuits 1 with a few new topics, principally dealing with how to handle multi-frequency circuits. All right, so any questions whatsoever? Rajan? 4. You've had 2 to this point, right? Yeah. So your next exam will be on steady state sinusoidal analysis. And that'll be, let's look at the syllabus to make sure, but I think you've got a couple of weeks. Yeah. So your next exam is due at the end of this month, effectively. So yeah, you've got plenty of time. We are right here with phasor circuit analysis 2 and multi-frequency circuit analysis. So like I said, instantaneous power, average power, maximum average power transfer. On Friday, multi-frequency power and effective values on Monday. Complex power and power factor correction next Wednesday. And then the Friday, next Friday after that is just a day dedicated to working problems if you guys want some more exposure to how to apply all those complex power relationships. I give us a day specifically dedicated to working problems because on that lecture on Wednesday the 20th, I hit you guys with just an absolute ton of equations and we don't really have a lot of time to put them into use. So I dedicate a day to using them. And then the following week before your exam, we're going to talk about filters. I'm not going to test you on the filter material. There will just be a homework assignment and a design problem associated with that stuff, but it's not going to show up on your exams. It is tangentially related to steady state sinusoidal analysis, which is why I lump it in with that material. And then we end the class with our discussion of 3-phase circuits, which is really just a continuation of what we're doing today. So I ask again, is there any circuit analysis techniques that you guys would like me to review for the remainder of this class period? All right, well, I hope you have a great rest of your day and I will see you on Friday.